we can do that. I use this linear approximation a lot in my calculus, and I realize that this is also a very, very powerful statement, a powerful tool to understand this Cauchy's formula. It is the right way to see, especially it's going to prepare you for the next part, infinite series and things like that. So what was the condition put on this Cauchy's formula for let f be what kind of function? Continuous, right? Not continuous. It has to be analytic now, so that you have Cauchy-Gaussat applied, right? Analytic on certain region R, that everything is taking place, and the statement is that f of a is equal to 1 over 2 pi I f of z, and c is inside that region, g minus a and dz. That's the statement. And here's the proof. F is analytic, and this C right now has correctly oriented around z equals a, and it encloses that z equals a. That's the situation in here. What if it doesn't enclose it z equals a? What's the answer? Answer is not fa. Answer is 0 because of what theorem? Cauchy's theorem. This is analytic. This guy doesn't enclose z equals a, then there's no singularity inside. So entire thing is locally inside that. It's analytic, therefore it's 0. If it encloses there, then it becomes a singularity in there, and it becomes that problem. So the idea is that kind of look at this f of z in terms of Taylor series. We don't have any result about the Taylor series, but just knowing that this is f of being analytic, we can still write following statement. This function here, f of z minus fa, divided by z minus a. A is z is in that region, maybe it's enclosed region in here, okay, and z is never equal to a, so that this one is defined, okay. Does anybody know how this one behaves? This one looks a lot like the definition of what? Very good. Mean value theorem. Another thing. Derivative. If you take the limit, it becomes a derivative. But yes, mean value theorem uses this thing. So what does the derivative says? This one exists, and why does that exist? Because f is analytic, and that one is denoted like this, f prime of a, right? But without the limit, it's not exactly equal to f prime of a. Is that right? So what is that rest of the part? It's slightly different, so I'm going to call this an error term, ez. All right? So how is this ez defined? Ez is well defined everywhere except z equals 0. Z equals a here, right? Z equals a, left-hand side is undefined, so this is undefined. But what we know is that as z approaches a, what happened to e of z? What do you know about that one? Approaches 0. Do you see why this approaches 0? This whole thing approaches f prime of a. That's the analytic statement, right? What could happen to the other remaining part? It has to approach 0. This is the analyze statement of a same old statement. Limit of this one approaches f prime of a, written without limit with the exact idea. All right? There's no Taylor series. It's very definition of differentiability in there. All right, so if you solve this like this, f of z, and you multiply that in here and move this one to the other side, so it looks like f of a. You see that f of a there? Multiply z minus a both sides, then we have f prime of a, z minus a, plus e of z, multiplied by z minus a. Correct? Do you think the e of z is a continuous function? is not defined as z equals a, but except that region, do you think is a continuous? Think about what E of z is. E of z is this quotient minus a constant, right? Isn't that what that is? The functional part is g minus a, and f of z. Is f is analytic, is a continuous, and z minus a is a continuous function. Is quotient of two function being continuous? If you avoid that undefined region? Yes, right? So a of z is a continuous function. And the behavior toward to that e of z equals a is a 0. And it is not defined as z equals a. This is called a removable singularity, is it not? Around it, everything is well defined, is going to 0, right? But at that 0, the behavior is very good, but it's undefined at that z equals a. But if you redefine that piecewise at z equals a to be 0, then it completes it, right? If this behavior is pole, then it's not removable. You can redefine it. So I'm going to use this e tilde of z so that it's actually defined. Okay? We don't know if it is analytic, but it's certainly continuous, and now it's defined equals a. The analytic part of the tilde 0 is, you have to be a little bit careful. If you use and replace it here, and it shows you what's happening. Okay? So I'm going to write down here. This integral without this 2 pi I, I'm going to relate it 1 over z minus a, f of z multiplied dz is equal to 1 over z minus a multiply to all these parts, f of a plus f prime of a, z minus a plus z minus a there, same copy, times e tilde is continuous and becoming almost 0, like that. By Cauchy-Gaussat theorem, as long as this one enclosed and doesn't pass through a, doesn't matter which circle you choose, it's going to be the same value, right? See that? So we have a freedom of choosing this c. Everything, no matter which one, as long as it's enclosed, is going to be the same. But let's look at this part in here. You distribute it here. You see the f of a picks up into z minus a. I'll lift it up in here. C dz. You see that? Before that was fz. Now it's a constant, right? You see that? It's a constant. Next part is that c and z minus a cancels, right? It's just a constant f prime of a. dz. How about next one? Z minus a and z minus cancels, and just e tilde of z dz in there, right? Did I distribute it correctly? So does anybody know what happened to this guy? Integrate this loop of what kind of function in there? Analytic or not? It's a trick question actually. It's a constant, right? Constant is therefore it's analytic. So what happened to that value, entire thing? Equals that's the antiderivative. That's right, antiderivative. So if you subtract beginning and end point the same, right? What happened? 0. Loop analytic function is a 0, right? How about this one? F of a is a constant, right? Before it was f of z. Now f of a is a constant. Can we pull that out, f of a there? And just integrate 1 over z minus a, where c is going around this a? We know this thing, right? What is that? 2 pi I. We got the answer right there. 2 pi I f of a. Isn't that Cauchy's formula? Right? So you got to show that this one, this weird thing in there. Continuous function. And the c, you have a freedom. There's no c in here. You can choose any c in there. This is a bit strange part. But so c they choose. The strange thing about this one is as we vary this c, this value doesn't change. What theorem is that? The left-hand side is our original problem, as with this very C contract or not, it doesn't change its value. What theorem is that? Cauchy-Gosal theorem. And these guys are fixed. It's not changing at all. No matter what the C is, this is fixed. And this part, as you dilate the C, we know this guy doesn't change. This is a constant. Without even knowing this E tilde is analytic. We only know it's a continuous, but by Cauchy-Gosal, we know this guy is always a constant number. All you have to show is that this is actually constant, is a 0. Right? A strange argument. But what they do, let me create a little space in here. I'm going to do that here. C is over here. Any C you can choose. Let's say it's a radius r, and we're thinking about measuring this quantity there, dz, and C in there. And we want to show is 0. So the usual technique is that we're going to actually simplify this absolute value, and as absolute value go inside the Riemann sum, if you look at Riemann sum carefully, that becomes a little bit larger. Integrating and changing the sign later, and everything positive, it gets a little bit bigger. But it's still good enough to show that. This one, it turns out, this function, if C is really, really small, if the radius is getting smaller and smaller, and this is continuous, and inside this, or going around this, looping in here, is all parameterized with respect to t. So this is a like closed interval. So this has a maximum value, which is called extreme value theorem. So this one is no more than certain maximum value m, which depends on this r, if you dilate the circle. So you can replace this functional part with a one constant, is going around c to dz, which is a positive maximum value around that circle. It exists because of extreme value theorem. It depends on your radius r. You can see as and this is constant now, you can factor out mr and the c dz. I forgot to translate the dz dt and dz dt here, so that has to be dz dt from 0 to 2 pi. That's one thing we have to do. So about the delay is a 0 to 2 pi. So we pick up 2 pi I there again, mr times 2 pi I. If you do this parametric, if you use the parameterization calculate, we can show not exactly, but is less than this some number times 2 pi r. This mr is a maximum value of this one, and as we get this m smaller and smaller, and of course the mr approaches this value right there, which is E tilde of A. Does anybody remember what E tilde of A was? Yeah, it was approaching 0, and we filled in that E tilde of 0. The removal singular, that approaches 0. Therefore, this guy here is a 0. So mr, the maximum value around that little loop, is approaching 0. Funny thing again is that this is a constant. And we got an upper bound that always works that pushes down to 0, and this constant had no choice, must be 0. If not, this upper bound will get arbitrarily small and go below the whatever number you have it there. This is an interesting argument. This is a constant. We found arbitrarily small upper bound. The conclusion is that that constant must be 0. Okay, so that's why this constant is not approaching 0. That's a funny part. This is not approaching 0. This is a 0. But we use that squeeze theorem to conclude that constant is 0. Sorry about this delay. I'll stop here.